Hey guys, welcome back. We're going to start talking about circular motion. You have the notes for this if you want to follow along. And I'm going to try to connect again what we've previously learned to what will be new information. So first, let's start with something we know. So in simple terms, what is the definition of acceleration? The definition of acceleration is a change in velocity. How can velocity change? Well, it can change in two different ways. Velocity is made up of a magnitude which is the speed, so it could go faster or slower. But the second part of it is the direction. So in the previous section, we talked about what it would mean if we were changing the speed faster or slower. And for those type of problems, we used F net equals ma. Well, now we're going to talk about a change in velocity where we're changing the direction. So acceleration is a change in velocity. Velocity has speed and direction, same as magnitude and direction. If the direction is changed, the velocity is changed, and you have acceleration. Your speed could be constant. All right, so hopefully you'll be able to read that. It's kind of small in there. So I have the ladybug that is turning first counterclockwise or anti-clockwise if you're in Great Britain. I draw an arrow on the diagram to represent the velocity vector of the ladybug as it spins counterclockwise. So I give you guys a second to write down your prediction for that. So when it's at that point and it's spinning counterclockwise. All right, so I'm going to show our velocity vector as I spin it. And I will try to pause it at that point. And your choice should have been that at that point, the velocity was pointing almost straight up. So a correct arrow would have been straight up like that. All right, so in the next one, I want to draw an arrow on the ladybug. Now it's spinning clockwise. What would the direction of the acceleration be at that point? So going in the opposite direction, what's the direction of the acceleration? So I'm going to take this and spin it this way now. Let me go a little faster. And I'll pause at the same spot. Oh, no, I missed it. And it should have been towards the center. So towards the center. Our acceleration was towards the center. So at that point, it should have been towards the center. All right, so now I'm going to put the green ladybug or the green beetle outside of the ladybug. But they're sitting on the same disk. And again, I'm going to spin them clockwise this way, and I want you to draw arrows that represent how their velocities relate to each other. So the length of the arrow is important. Okay, I'm going to unclick acceleration. I'm going to put, whoa, that guy on the outside. I'm going to click show velocity vectors. And I missed the pause. And so you should have drawn, if I could put this, can't quite get them right on the outside of it, but they should be pointing in the same direction if they're in line with the radius, but the one on the outside should have had a longer arrow. So drawing our arrows on this. If that one was that long, this one should be long. All right, now I'm going to put the green bug closer to the center, still trying to put it in line. Oh, why don't I make the green bug green? And now I'm going to spin it this way, and I want you to draw velocity vectors that represent what the ladybug looks like when it's spun the opposite way. So counterclockwise. All right, so I'm going to stop it, and I'm going to go this way. Now, if it's closer to the radius, it's going to be a shorter arrow. So at this point, if they're lined up, they should both have arrows that are going in a straight line. This one is shorter than that one. All right, how about their accelerations? So now I'm going to put the ladybug further away again. And I want you to draw accelerations for them going clockwise. Put him further away. That lined up pretty good. Make it bigger. And so we should have had the green beetle with the longer arrow. They both are going towards the center. The green beetle had a longer arrow. So draw. This one went towards the center. This one went towards the center, but was longer. All right, now I'm going to go counterclockwise, and I'm going to put the green beetle closer to the center. And again, I want to draw accelerations for each of them as they spin counterclockwise. So I don't know if you can tell, but they're still both going towards the center. The ladybug has a longer arrow in the same direction. So we have a short arrow and we have a long arrow. All right, some questions from what we've seen. Number one, in what direction does velocity point in a circular motion? In a tangential straight line. So at whatever point you are, your velocity is trying to go into a straight line. That's what the first law tells us, that an object in motion wants to stay in straight line motion. Number two, in what direction does acceleration point in circular motion? Towards the center. It turns out that the word centripetal means center seeking. Number three, why did the bug that was farther away from the center have a longer V or A arrow? It was traveling a larger distance in the same amount of time. Number four, would you expect net force to point in the direction of acceleration or velocity? So remember our prediction with the blue and red guys, and they were pulling the taffy? What did force always agree with, acceleration or velocity? So force always agrees with acceleration. So our net force is always going to agree with acceleration. So where we have a centripetal acceleration, we'll have a centripetal force.